Okay, let me try to crank out another 10-ish problems. I don't know, 9 or 10 before I head off to bed. Here is 21. Get back over here. And what we're going to do with these, use green again, exact location. And now that, again, we'll watch this word carefully, of all relative and absolute extreme of the function. We've got this function. The quickest way to do this is to approach this graphically. So let me move this over a little bit. And then once we have the critical points, we'll be able to find the minimum and maximum. And we want to say whether it's what kind of minimum, relative or absolute, what kind of maximum, and whether there was no extrema at a given point. So, and remember, we always want to look at endpoints. Now, infinity is not really considered an endpoint because it doesn't end. But -1 we'll have to check, and then we'll see from there. So we will go ahead and graph this. Let's go to y equals, we're there. So we put in 3 x squared, or sorry, x cubed. Arrow down, and then minus 9x. So notice we don't take the derivative squared, though we do have to have it in correctly. You could also approach this, you could take the derivative and set it equal to 0, and that would give you the same things. What we're going to do is, what window do we need? Well, our domain's going from -1, so we don't need -2. Let's start at -1. And since we're going to infinity, that's quite a ways out there. I don't know that we need to go that far, but maybe go to 25. I think that's pretty far out. And then we've got the y going from 0 to 40. Cubics, the way they kind of could look kind of like a saguaro cactus with one hand up, one down. So I'm going to go, why don't we just go with -40 to +40, and hopefully we should have it covered in there. So yeah, we got our thing, we got our little saguaro dip here. So we could actually, we don't have to go out that far. We'll see things a little bit better. Going 1 to say 10 looks like it'll be plenty on the x direction, and the y direction maybe -15 to +15 will get the job done. Okay, so we're looking, this gets us zoomed in a bit. So we do see an endpoint here, so that looks, it's definitely at least a relative minimum. It may be an absolute minimum for this domain, and then it shoots off forever. And then we see this bump here, a relative maximum. Okay, so the quickest way to find -1, one of the quickest ways, is to go to the table and scroll to where x is -1. Yes, could have been quick if I would have had this my table set up. So -1 is -12, and they want us to list these generally from the smallest x to the largest. So -1 to -12, and we'll hold up judgment. We know that's a minimum from the graph. We can see it right there. So we'll put a minimum. It may be an absolute minimum if it matches up with the second one we're going to find. So then we return to the graph. So we found that point is -12. We're going to find this going in the order. Second calc, we're going to look for a maximum. That's a number 4. And notice it asks for a left bound. Right here it tells me I'm at x is 4.5 and y is 91. That's why I don't see anything. So I right arrow back, and in a moment here, I should be able to see, maybe I need to start seeing my little cursor spider. It looks like a little spider to me. It kind of crawls around there. That's what we call it. One of my classes named a spider Simon the Spider. Come on. does take a little bit of time, but your calculator probably is going to work faster than mine is working right now. So the left bound, we have to be on the left side of that mountain. So there's the summit. We're up there. We're going to come till we're down on the back side. So watch that little cursor. This is probably good enough. I always like to overemphasize. I hit enter. Now it's going to ask for the right bound. I take this cursor and I walk it to the right. So I have to go over the top of the mountain, come back the other side, and then it's probably not the calculator, it's my computer that's slowing down. It says, let me go to sleep. There we go. We hit enter, and then for the guess, we hit enter. It looks between those 2 points we made, and it found a maximum. Now this x value, be careful here. This e to the -7, that's scientific notation. So that's times 10 to the -7. So we're going to move that decimal place. This is what it ends up looking. We move that decimal place 7 times here. So we get 0.0. We get a bunch of zeros. What we want to see is that that really is x equals 0. Okay. And the same thing, it's really y equals 0 because there's like 11 zeros in front of here. We have to move the decimal 12 places. And so you have to fill it up with 11 zeros. It'll round to 0. It's the 0.00. Now this one we can see, since we're going to go to infinity, it gets pretty high. This is not an absolute maximum, definitely not. It's a relative maximum. So we would just label that as a rel max. Okay, and we would do there's a drop-down list right there. So that one is set in stone. We're good. We just need this last one, and that is a second calc minimum. So we go to number 3. And again, this thing is going to be a slow walker. See, I wonder if I hit the arrow keys. That seemed to work, sort of. Maybe I should restart this thing. It's just, okay, so I'm going to put a left bound there. I'm at the left of the hill. And then I got to come to the other side, to the right of the minimum point. Maybe if I just don't hit it so many times in a row and just be patient. Sometimes that's what we need, is patience and kindness, and it gets us a lot further than being aggressive. And then enter again for the guess, and it's going to give me my point right there. And again, I'm going to round this to 2, -12. So what I see is that I've got +2, -12 is another point. And what this is, it's an absolute, not maximum, absolute minimum. Sorry about that. And so is this one. This is an absolute minimum. Okay, because it's -12 is the lowest we go. Okay, notice how we did this all graphically, especially for testing. That's the way I would suggest it. We should know how to take the derivative and then set it equal to 0 for times when we can't graph it. But if we can graph it, let's take that choice. Let's learn, like in ancient India, they learned multiple ways to do problems, and they would always shoot for, well, what's the easiest way? What's the simplest way? What's the most straightforward way for a particular problem? That's what they would use. And I think that's the wise way to go about it. Okay, so that works for this one. And we're going to see, we're going to keep moving on with these, graph them, and then and find the max and mins. And again, it's helpful. They're telling us there's probably 3 of them. Again, it could be that, well, we could have a critical value that's not an extremum, but we'll just see. So we're going to graph this. So we get our graphing calculator back out. We go to y equals, clear this one out. And so we go with 5. We do a parentheses. Now, just for ease, I'm going to show you, if you've got at least the newer, there's a F1 here. It's green. So if you go alpha F1, this is a cool little thing that happens. You can actually get a fraction template. So that's number 1, numerator over denominator. Watch what this does for us. it gives us, so we don't have to worry about parentheses. X squared plus 1 over x squared minus 1. Now, you could probably, yeah, the bottom is a, oops, sorry, that's the one I want. And then we want to make it squared minus 1, subtract 1. Make sure you use the right type of negative here. And we come over here and then we put our other parentheses. Okay, so that's t squared plus 1, t squared minus 1. That's all looking good. Our domain's going from -2 to +2. So when we come to our window, that tells us to set our x and y, or at least our x minimum, x maximum, -2 and +2. The other thing I'm going to, and then our y's, I'm going to leave it at -15 to +15. I think that'll be plenty. We might be able to zoom in. While I'm going to go to table set. I'm going to change this. It's at -1. Notice the table is changing by 0.25. Let's have it change by 1. So if we're going to end up using it, it's a lot easier to use. We'll hit the graph button. We see this going that way, that going this way, and then this coming this way. So so from -2 to 2. Now the thing is this is only going to +15. If we went higher, these probably go off to infinity. These are probably, not just probably, but they're asymptotes, right? Because you get x plus 1, x minus 1. So at -1 and +1, we're getting asymptotes. The top doesn't factor, so that's why those are still these asymptotes. So notice we get, so these are going to shoot off forever. Those are not going to give us a min or a max. And these are going to shoot down forever. So the range is going to go from -infinity to +infinity. There is no absolute maximums or minimums, but there are relative ones. And what we can see is for this area right here at the endpoints, we definitely have 2 relative minimums and we have a relative maximum right here. Don't be fooled by this because we could go down further. These kind of continue to go down. So let's find those are 2 endpoints, -2 and +2. Those are going to give it to us. So now I'm thankful that I changed the table because it's an easier way to look it up. -2 is 25/3, and they wanted the exact location. So I wish I could say that I had thought this in advance, and but I remember when you use that function, that fraction thing to put in a function, it also gives you your answers in fractions. -2 comma 25/3. Otherwise, you would have had a repeating decimal 0.333. And since they want exact, no matter how many 3's you put, it'll still mark it wrong. And then you'll contact me and say, I know I got the right answer. But you need the exact location. That's what I'm going to assume is happening here. And again, what is this? This is a relative minimum. So that's this one here. The middle point, well, actually, while we're here, we'll go ahead and get this one down here. We know that at 2, it's also 25/3. And that's also a relative minimum. Okay, so those are both relative minimums. They're not absolute minimums because we do go down to -infinity. So let's get this middle point here. We'll do that from the graph. And we could see x is equal to 0. So we could also just look it up on the table. We'll do it both ways. It looks like -5. So 0, -5. We're going to look it up just to be sure. And what that one is, that one's a relative maximum. So this one here is going to be a relative maximum is what we want to choose. But let me go second calc and look for the maximum. And again, we'll just go a little bit off and a little bit down the hill so I don't have to go too far. Enter. I'll show you that you can do this. I have to go till I'm at least to the other side, and it's a little bit lower, and then I hit enter. So you don't always have to go a long ways, But yes, remember this x, it rounds to 0 because it's e to the negative 10. So it's 6 zeros. So this will round to 0, and this is negative 5, just like we thought. Okay. Done. Okay, we're going to keep running through these. 23. Okay, now we've got a slightly different type of problem. We've got a cost function. So here's our cost function, and that's the dollars to manufacture X units of a device in an hour. So that's per hour, X units per hour, or yeah. How many devices should be manufactured each hour to minimize average cost? So remember, average cost, and they use that little bar over the top. If you're doing statistics, you'll maybe be familiar with that. That's the function c of x over x. So each one of these gets divided by x, right? There's a big, we just really need to divide this by x to make it the average cost function. If we're taking the derivative, we're going to want to distribute this x to each of the terms. So we get 676,000 x to the minus 1, because there's no x there, so we bring it up there. In the middle, the x's cancel, they become a factor of 1, so then we have a plus 160 here in the middle. And then the last one, this x cancels with the x squared, so we've got plus 0.001x. Okay, so that's our average cost function. And we want to maximize this. So what we want to do is take the derivative and find where it's 0. We could go ahead and graph this, but this is a pretty large number. There's 160. I might have some problems getting the window just right. So maybe with this one, let's go ahead. I think it'll be faster if we take its derivative. The derivative of the average cost function. And so the negative 1 comes down. 676,000. Subtract 1 from the exponent. That becomes x to the minus 2. Derivative of 160 is 0 because it's a constant. And then the derivative of the 0.001x is just going to be plus 0.001 x to the 0 power. We set this equal to 0. So I'll just squeeze it in there. I'll take this out. So now we've got set equal to 0. Add this first term to both sides. And as I do it, I'm going to move the x squared down. So we get 676,000 all over x squared equals 0.001. Multiply both sides by x squared. And we get 676,000,676. So my major problem is copy errors. And then we divide both sides by 0.001. So that gives us x squared. Now when you divide by a decimal, it actually makes the number bigger. So we're going to get bigger by 1,000. So this is going to be 676, 1, 2, 3, 1, 2, 3. And then we can take the square root of both sides. The negative would not make sense because I would be producing negative of these. But let's go ahead and go here. Square root of both sides is going to give us x equals, actually I did it a little earlier. Where's my calculator? Disappeared. There we go. So now it's there. Let's go here. Go to the main screen. Let's clear it out. And let's see, what are we doing? Okay, which square root, which is, there it is, it's above the x to the minus 1. Square root 676. 1, 2, 3. 1, 2, 3. 26,000. 26,000 an hour. Wow. So we need to produce 26,000 an hour to minimize the costs. So we put that here. And so what is the resulting average cost of a device? So we plug in the 26,000 into the average cost function. So for each of these x's, we're going to plug in 26,000. So we've got 6, 7, 6, 1, 2, 3. And this -1 just means we're dividing by the x. So we'll just divide by 26,000. We're going to add 160 because remember, we're not using the derivative. We are using the actual average cost function. Add the 160. And then we're going to add 0.001 times 26,000. And we could have maybe done that in our head. I think that'll be 26 because you multiply by decimal, you move the decimals the other way. Anyway, it gives us 212. Okay, so that's average cost per unit. Make 26,000. Average cost is 212. Hopefully we can sell them for maybe double that or more. How does the average cost compare to the marginal cost, and find them by how they differ? Okay, so marginal cost, remember, is the derivative of the cost function itself. So we come back to the original function that they give us and ignore all this green stuff. Derivative of 676,000 is 0 because that's a constant. Then we have 160x, so that derivative is just going to be 160, x to the 0. And then on this back part, this 2 comes down, so we have plus 0.002x, 2 minus 1, okay? And so now we want to find out when we plug in 26,000 here, what is our cost? So our marginal cost at 26,000 is 160 plus 0.002 times 26,000. And plug that in. And then we're going to subtract whatever we get there, we subtract 212 from it. Yeah, that's good enough. You can see both. Okay, so we've got 160 plus 0.002, which would be 26 times 2, which would be 54. And it looks like we're going to get about 212, I think. 54? No, sorry, 2 times 26 is 52. So put that in there. And our answer, 212. So what they want here, though, is not, so the marginal is 212. And so we take the 212 of the average cost minus the marginal 212, and we get 0. Which I think we've done this before in another problem, and that's kind of typically what happens probably when you're minimizing, you're getting the minimum average cost. That marginal cost of producing the next one is going to be about the same. Okay, so more word problems here, more max optimizations. So I would like to take a rectangular garden. Okay, so rectangular is something like that abuts my house. So the house itself forms a northern boundary. So we'll put the house here at the northern boundary. Here's that. So here's the house, here's the door. And this is kind of the garden. And so we don't need a wall because the house itself is the wall. The fencing of the southern border costs 10 feet, $10 per foot, because it's right across from the house. And the east and west sides are only $5 because, again, they're in your peripheral vision. if I have a budget of 160, so budget's 160 for the project, what are the dimensions of the garden with the largest area I can enclose? Now, the thing, it kind of depends on your house, because if you make it bigger than the house, you're going to need some fencing on this north side, but we're going to assume that the garden area is smaller than the house, so that there is plenty of house to go around to enclose the garden. We'll just make our house a little bit bigger. So whatever we make with the garden, we're gonna use up our budget before we overrun the house. That's just something we have to make an assumption of. And then again, we want the largest area and we want the dimensions. So we want the base times the height. Area is equal to length times width. The cost of the function comes from the perimeter, but we don't need, we've only got 3 sides. So we'll call this the length. Each of these sides is a width, right? And this $5 is not that it's a width of $5, it's just that's the cost. So the perimeter that we can have is going to be, notice we're going to have two widths. We're going to have 1 length. That's going to be our perimeter. The perimeter determines the cost. And so the amount we can make here to 2 times the width is in every foot, right? I think they're talking about feet. A foot, yeah. Every foot is going to cost us $5. And on the length, every foot's going to cost us $10. Okay, so we get 160. 5 times 2 is 10. So we get 10W plus 10L. Then we're going to want to, because we want to maximize this function, we've got to get it in terms of just the one variable, either L or W, your choice. I'll subtract 10W from both sides. We get that 160 minus 10W is equal to 10L. So divide both sides by 10. And you get that the length is equal to 16. Distribute the 10 to both sides, to both terms, minus W. So this we can replace L with this. So we get that we can get an area that's equal to 16 minus W times W. Let's go ahead and distribute this. So our area is going to be 16W minus W squared. We're going to maximize it when the derivative is equal to 0, or at least we get a critical value there, right? So we can take this derivative. You could also graph this, but the derivative is pretty straightforward. So we get 16. The derivative of 16W is just 16 minus 2W. We set this equal to 0, and that will give us a minimum, a maximum area, because it's an upside down quadratic, right? It's going to go like this. So it's going to give us the vertex. I guess you could also find the vertex. Well, you'll see me this. If you remember, the vertex formula is minus b over 2a, something like that. So b was 16. This is a is 1, and you got, okay, so yeah, that's what we're going to get. So actually, I'm going to add 2W to both sides, just to show you can do that and then not have to worry about negatives. So 2W equals 16, and lo and behold, divide both sides by 2, you get that W equals 8. So we want the width to be 8, and then to figure out the length, we put in 8 for W, and you get 16 minus 8 equals our length, which is 8. So it's not a, it's a square. A square is also a rectangle, but it's 8 by 8. And then so what is the actual area? 8 times 8 is 64 square feet. So it's not that big. I mean, the house should be at least 8 feet wide, right? So you just didn't have much of a budget. So it's a little bit smaller area, not drawn to scale, that kind of stuff. So that's 24. Let's keep going. I'd like to get to 30 before we call it good. Again, these are going to be time consuming, but look at the ones you need to. You can fast forward to the ones that you understand, fast forward past the ones you understand. Okay. The fencing of the left border costs $5 per foot. The left border. So we've got this right triangle flower garden. The borders can be in any direction as long as they are on the right angles as shown. So kind of showing us here. So the left border costs $5 per feet. Same type of thing. While the fencing on the lower border only costs $1 per foot. That's cheap. Much cheaper. No fencing is required along the river because you want to have access to the river. You want to spend $140 and enclose as much area as possible. So you've got $140. Let's use it all. Let's get as much area as we can. And they do give us, since it's a right triangle, it is 1/2 the base times the height. Okay. Probably the base is going to be longer because it's cheaper, right? So you get better by going that route. So we've got our area function right here, sort of x times y. We could call either side, one side's x, one side's y. Doesn't matter which way you do this. You might do it the other way. So what I need to do is kind of figure this out in terms of left border, right, bottom border, garden area. Again, we got to get it down to one variable. And the trick is this perimeter here. The 140 comes from the perimeter. So what are we going to spend? We're going to spend whatever y is plus x. So we're going to do $5 times x plus $1 times y will be the cost. And we've got to keep that at 140. So not just a budget, but that's what we got. So we solve this. I'll solve it for y because we've got one y here. That makes it a lot easier. Minus 5x minus 5x. So we get that y is equal to 140 minus 5x. We can now substitute this in for the value of y down here. So we get that our area is x times 140 minus 5x, all divided by 2. We can distribute the x through. We'll get a quadratic, take its derivative, set it equal to 0. We'll find the maximum, and you'll see we're going to get a negative leading coefficient on the quadratic. So it becomes 140x minus 5x squared all over 2. We could distribute this 2, and so we get 70x minus 2.5, 5 divided by 2, x squared. And let's go up a little bit. We want to set that equal to 0 because, oh, wait, no, we've just simplified. This is still area. This is still area. We want to take the derivative of the area, and I'll give some more room here. So that's going to be 70 minus 2 times 2.5. So you kind of see now where that formula b over 2a, because it's a derivative. That's cool. 2 times 2.5 will be 5x. And then again, we set this equal to 0, add 5x to both sides. So you get 5x equals 70. And then we divide both sides by 5, giving us x, which we called our left border, is going to be 12, 14. Yeah, 14 times 5, that's 20, that's 50, 20, yeah, 14. So that's our left border. Our bottom border is going to be y, so we plug in 14 here, so we get 140 minus 5 times 14. 5 times 14 is 70. So 140 minus 70 is 70. So as we predicted, y is going to be the longer side, 70 feet long by 14 feet. And then the garden area will be 14 times 70 divided by 2. So come back here. Remember, it's not a rectangular, it's a triangular region. So we've got to get half the area. So 14 times 70 divided by 2. When you kind of working late night, you want to, it's not that late, but for me, I try to get to sleep early if I can, wake up early, and then we divide by 2. There we have it, 490 feet. Our beautiful garden, triangular garden with the riverfront. Okay, so that's how that one works. We had a similar one in the homework. So just more practice on these types. And the more you practice it, you'll get this rhythm down and you'll just kind of get into it. And when you see something similar on the test, and which you will, because the test is coming from these units, and we only have so many problems that we can give you, the numbers will be different. So you got to do your calculations carefully, but you practice all of these and you'll be well prepared. So remember, practice all these review ones in WebAssign, and as well as the review, the sort of the paper review or the static review that I've got already videos for, and practice them, see how to do them, come back and do them again, even though you know the process. That again reemphasizes it. Okay, so the price of video release of its Pride of Sons of Frank. The marketing estimates that at a price of P dollars, so we can sell this much. So this is a demand, but each copy costs $4 to make. So there's a cost. What price will give the greatest profit? So sometimes I read this backwards, but we're looking for profit. So I got to remember profit is equal to revenue minus cost. This is going to be our cost function, and they don't tell us any fixed costs or anything, but we do know that the cost function, P is the price. However many we make, Q is the quantity we're going to sell. So I guess we would probably make as many as we're going to sell. So however many we sell, this is going to cost us $4. So that's a Q function. The cost for Q. Let's do that. The revenue function, though, is the amount that we sell times the price. So it's going to be revenue is really Q times P. Well, what is Q? Q is this whole thing here. So let's get everything in terms of just the one variable. Revenue is going to be 300,000 minus 10,000 P, times P. So we could distribute that. Cost is actually what's Q. Well, it's going to be 4 times Q, which is 4 times this. So cost ends up being 4 times 300,000 minus 10,000 P. Okay, so we could distribute that through and we'll get our cost. And then profit is revenue minus cost. So, and we want to get the greatest or maximum profit. So profit is going to be equal to, again, remember it's revenue first. I see some of you switching the cost, you cost minus revenue. That's not the way to run a business. You want your revenue to be bigger than your costs. And the costs are what's negative. So let's go ahead and distribute this P. So we get 300,000 P minus 10,000 P squared. then we're going to minus, I'm going to distribute this 4 times 3 is 12, and then all those zeros, so 12 million. And then 4 times negative 10, it's going to be negative 40,000 P. We can distribute this negative. So I'm going to just change color to help out here. So this will be negative and this will become positive. So let's combine like terms. I've got 40,000 P, a positive 40,000 P, and I've got 300,000 P. Let's write that as 340,000. 340,000 P, like terms here and here. I could put the quadratic first, but I didn't, so I'm just going to leave it here. And then we've got this minus 12 million. It's quite a production. It was big time. Fixed costs of 12 million. Variable costs of 40,000 per dollar of price. That's what it's telling us. So this is going to be our profit function. What we want to do is we want to take the derivative of profit and then set it equal to 0. So when we take the derivative, this becomes 340,000 P to the 0 power minus, so the 2 is going to come down. This is going to be 20,000 P to the first power, and the derivative of a constant is 0, so that all drops off. Interesting why it doesn't, but it just tells us, that tells us something. So then we set this equal to 0. I'm going to add the P part to both sides, so we get 340,000 equals 20,000 P. Divide both sides by 20,000. And we'll have the price that gives us the maximum profit. So what we can do is just do a quick, the zeros sort of cancel each other out when you're dividing. So those are all gone. 34 divided by 2 is 15. 30 divided by 2 is 15. 4 divided by 2 is 2. 15 is 17. So you should charge $17 and we will maximize profit. Again, we could have graphed it, but this is one, 12 million, getting your window be down. Anyway, this is how we can use the derivative. When the derivative is equal to 0, we get a minimum or a maximum. And again, in this case, we know it's a maximum because it's a quadratic with a negative coefficient. So we know it opens concave down. So we know that vertex is going to give us our maximum. 26, a few more. Okay, worldwide annual sales of a product in 2013 to 17 were projected to be approximately this amount. So again, Q is sort of a demand function. This is how many millions of units we sold, and it gets sold at price P. What selling price would have resulted in the largest projected annual revenue? So notice for revenue, we do not need the cost. Revenue is simply the amount, in this case Q, times the price. Well, let's rewrite Q as this function so that we only have one variable. Okay, so we get minus 10P plus 4,380 times P. Okay, so amount times the price, that's revenue. Let's go ahead and distribute it out. Minus 10P squared plus 4380P. We want to maximize this so we can take its derivative. You could also graph it. You could also see, well, it's a quadratic, so all I got to do is find the vertex minus b over 2a. Because that gets to be when you recognize it's going to be a shortcut. I'm going to do it both ways, because if you don't see this and you don't remember this, but I want, for those who do remember, I want you to know. So B is the number in front of the single variable, the 1 to the first power. And again, that's minus over 2a. A is the 1 in front of x squared. So that's 2 times 10 minus 10, actually. So a negative is going to make it positive. So that's 4380 over 20. Can we take that and then cut that in half? That's going to be 200. And half of 38 is going to be 15 plus is 19, 219. Okay. How did I get that? Well, again, I take its derivative. So the derivative of r, 2 times 10 is negative 20. You see where that's where that 20 came from. P plus 4380, p to the 0 power, because that's the derivative. Set it equal to 0. And again, what I do is I'll bring the negative over. So minus, all right, I could subtract this. So we get minus 20p. I just make it look more like the other one that we have, 4380. So there's the minus b divided by 2 times a, right? That's where that 20 came from. So again, we get p equals 219. What would have been the resulting projected annual revenue? So what we have to do is we've got to come back to the revenue function itself. So that's why it's good to write it down. We're going to plug in this price of 219 into here, and that gives us the y value, the y coordinate of the vertex. The vertex is what gives us our maximum. And let's just go ahead and plug that in as we're at here. Move over here, please. We will put in negative 10 times 219. That's what we came up with. 2 different ways, 2 different times. Squared plus 4380 times 219. I'm just plugging in the price each where it's supposed to be. And we made $479,610, which sounds like a good deal. But again, it does depend upon what our costs were. Oftentimes we could have great revenue, but what was our cost to produce things? That will determine whether we're a profitable business or not, whether we made money, lost money. You all know that. Okay, so that was 27. Got 2 more. And okay, now we're into easier times. Okay, we're into calculating the second derivative. So this must be 12.3, I believe, is what we're into now. So the second derivative, so what we do is we take the first derivative and then we've got to find the second derivative, right? So I'm going to do it this way. I'm going to rewrite this as 2 times x to the minus 1 minus 5 natural log of x. We take the derivative, and fortunately we don't have any product rules or quotient rules, but the negative 1 comes down, so that's negative 2x to the minus 2. That's the first part. Over here, the negative 5 is a constant multiple, so we get negative 5. Derivative of natural log of x is just 1 over x, so we'll put 5 over x. And looking at that, I'm going to rewrite this derivative as negative 2x to the minus 2 minus 5x to the minus 1, so that when we go to take the second derivative, the derivative of the derivative, it's a lot easier to do. So the negative 2 comes down. Negative 2 times negative 2 is positive 4. Subtract 1 from the exponent, we get negative 3. Here, bring the negative 1 down, so negative times a negative is positive 5. X, subtract 1 from it, is negative 2. So that's the function that goes there. nothing much more to do with that one in a row. Got a couple more, and then I'll stop for the evening and maybe get the rest done tomorrow sometime. So now we've got position function s, and we want to, in feet per second, we've got a particular time, t equals 16, and we want the acceleration. Remember, acceleration, they show us here, is the second derivative. So what do we have to do? We have to take the first derivative to get to the second derivative. So square root of t, we're going to write as 0.5, and that's going to be plus 2t squared. We'll take the first derivative, which is velocity, but we don't really care about that because that wasn't what the question was. So the 0.5 comes down, subtract 1 from it, so we've got a minus 0.5, or 0.5 if you want. The derivative of the second term, 2 times 2 is 4, t to the first power. So that's our derivative there. Our second derivative, the derivative of the derivative, which is going to be our acceleration, is the negative 0.5 comes down, and we're going to get negative 0.25. 5 times 5 is 25. The 2 decimals move it over. And then we have t, we subtract 1 from it to the minus 1.5. When we take the derivative here, the 1 comes down, so we get a plus 4, t to the 0 power, so that part's gone. So that is our derivative function. That's what we put in here. Find its acceleration at this time. We plug 16 in for t. So we're going to do that. So we get minus 0.25, 16 to the minus 1.5 plus 4. Now you could do this. So square root of 16 is 4 times 16. But, you know, probably the fastest way, just go ahead and put it all into the calculator. Minus 0.25 times 16, because we're going to divide by this anyway, right? Raised to the negative 1.5 plus 4. It's 3.99. Did they tell us how many decimal places they wanted? Seconds. It's so many feet per second. Let's go with 1, 2, 3, 4, 5. 5 decimal places, and then just not really any rounding. Let me do something. I pulled it up so I could do a quick assignment preview. Oh, it's over here. So that you can't see it, but I can see it. And let me come down. I had to give me the answers so I can check them as I go. And we've been doing pretty good so far. 29. Now they've got an exact value. I think we're kind of close. Let's see, what are we? So they rewrote this. Instead of 0.25, they put a 4 down here. T to the 3 halves. And they left it all as a fraction. That's the things usually this is 1/4. (16 to the 3 halves) plus 4. And if we work out just the bottom part, or we could just work out this part here. Actually, it's probably just to find what the denominator is. I think it's going to be 256. So that's 4 times 16. And we could just raise it to the 1.5, or you could do the 3/2, right? I'll just do 1.5, get the same answer. So let's see this. I bet you that's 256, right? 256. 1 over 256 plus 4, and we want a common denominator, so we've got to multiply 4 over 1. We've got to multiply by 256 over 256. And again, this is negative. So that negative. Okay, so 4 times 256 times 4 is going to be 1024. And you're going to subtract 1 from it. So this is 1024 over 256. And this is minus 1 over 256. So just so that you know, if it's a multiple choice, so that's the exact answer. And that's what so if you've been working on this, that's what they're going to want to see. I'll bet you they're counting these ones wrong. It might not. Sometimes they'll accept these decimals. But, and if they didn't accept this, what they were looking for, at least what the answer that they show is 1 over 4 t to the 1.5, or the 3/2. The 3/2 is what they showed, plus 4. Okay. Process though. And we've got, I think, one more second derivative, and this one will be pretty nice and straightforward. So this one we don't even have to do too much with. We'll just go ahead and leave it as is. So the first derivative, chain rule, we take the derivative of the exponent is just going to be -1. E to the minus x. Derivative of e to the minus x is its own self, right? Derivative of e to the x is e to the x. So now when we take the second derivative, it's not going to change much. This negative, again, it comes down because the derivative of the exponent becomes -1. -1 times -1 is +1. So we get e to the minus x plus e to the x. I think this looks like deja vu, like we've done this before. So that's that one. And that's what they have, right? Second derivatives. So I'm going to process these, get this uploaded, and then we've got one more series, about 10 more problems, what, 31 to 41, maybe that's, however they are. Is that 10 or is that 11? It's too late to count. Okay, we've got about 10. So we'll end it here. Stop the recording.